So I'm leading a team from UCLA, University of California, San Diego, and University of Maryland to look at whether seeding wintertime mixed-phase clouds, whether those can be used to cool the poles. So we're taking it down from the stratosphere, down to the boundary layer, and also looking specifically at the poles, right? So a bit of a change in pace here. Now, there's a lot of new faces here relative to November when we had the kickoff meeting. So I'm going to first explain quickly the basic idea of mixed-phase cloud thinning to get us all on the same page. This was proposed a few years ago by Diego Villanueva and Ulrike Lohmann. They have another grant. We've been collaborating with them. Diego's giving the next talk after the break. So the idea is to target these mixed-phase clouds. They are very common at the poles. This is a picture on the right that I took from an airplane a few years back. You see these sheets and sheets of clouds covering the boundary layer. So these clouds consist of ice and supercooled water. So this is water that would want to freeze if it can get over the energetic barrier to do so. And so that energetic barrier can be lowered by ice nucleating particles, so usually solid particles in the atmosphere, like mineral dust, for instance, also some biological particles. So these are on the boundary layer, so cloud tops mostly below 3 kilometers. And so they exist in this temperature range between -37, at which water doesn't need that nucleus to freeze anymore, and the freezing point. So they're quite common. Like I mentioned, this is the fraction of mixed-phase clouds in the Arctic winter on the left and the Antarctic winter on the right. Okay, so the idea then of mixed-phase cloud thinning is to add ice nucleating particles to these clouds to help this freezing process along. So transitioning the cloud from the pristine cloud on the left to the seeded cloud on the right. And so what happens when you get ice formation in these clouds, the clouds are basically saturated with respect to liquid water. So when you create an ice crystal, the vapor pressure over the saturation vapor pressure over an ice crystal is lower than it is over a water droplet. And so these ice crystals find themselves in a super saturated environment. So they grow really fast. And so you end up basically consolidating the condensed water into fewer larger particles. So those have a lower cross-section, lower cloud optical depth, and this can kickstart the precipitation process, therefore raining out these clouds and possibly reducing the coverage of these clouds. Okay, so why are we talking about this for climate intervention then? How can we actually generate a cooling with this? So on the left here is the schematic for the polar nighttime, which is the season we'll be targeting. Right, so we have long-wave radiation emitted from the surface. Some of that's going to be absorbed by the atmosphere. The atmosphere is itself emitting at a lower temperature, so we get less outgoing long-wave radiation than is emitted at the surface. If we now add a cloud, it does two things. One, if you imagine yourself in the wintertime staring up at the coldness of space, there's not a lot of thermal radiation coming down. So if you now add these clouds over your head, you have these radiators essentially over your head. So this adds a lot of warming for the surface budget. Also, these clouds absorb the long-wave radiation coming from the surface and then emit themselves at a lower temperature, so they reduce the outgoing long-wave radiation. So these clouds warm both at the top of atmosphere energy budget and at the surface. This is for the pristine case. If we now seed these clouds, they become less optically thick, right? And they have lower coverage, so per the schematic on the right here. And so that thus reduces the warming we experience at the surface from these clouds, and also it intercepts less of the radiation emitted from the surface, so it also reduces the warming effect of the clouds at top of atmosphere. So it cools at both the surface and at the top of atmosphere. Okay, so our project then is to determine whether this is actually a viable idea or not. Can we actually reasonably cool the poles with this? And if so, it could have some substantial advantages perhaps over, for instance, stratospheric aerosol injection, because it's a regional method and it messes with the long-wave component of the radiation budget, as Gabe talked about, which is a closer match to the problem. So the questions we want to answer then to determine this is, would seeding these clouds indeed produce a cooling? Can we show that it does? Right now we have model evidence for this, but can we show that this is actually happening in nature? If so, how much cooling could it provide? And if that is substantial enough to be climatically relevant, what would the benefits and the costs of doing so be? And last, of course, is this technique even feasible? Is it economically and technically feasible? We'll leave that for another grant to study. And we're going to focus on the first three here. So first, figuring out of, okay, if we see these polar nighttime clouds, would that indeed produce cooling? Now, nature has gifted us two wonderful natural experiments for this. The first one is that there's a large contrast in the aerosol population, the aerosol mix, between the Southern Ocean, which is probably the most pristine environment on the planet, and the Arctic Ocean, which is under the influence of the Northern Hemisphere major deserts, Sahara, Asian deserts, and also, of course, anthropogenic pollution. So from this contrast in the aerosol populations, we can perhaps tease out what the effect is, what the effect would be if we took the Southern Ocean clouds and we seeded them to the aerosol mix of the Arctic Ocean, right, where we have a lot more aerosols. The concentration of ice nucleating particles there is something like 1 or 2 orders of magnitude, larger. We can see this also in the clouds themselves already. The lower left here is the fraction of clouds at minus 20 degrees that are supercooled, and so that are not frozen. And you can see that in the Southern Ocean, that's a lot more red. So there's a lot more clouds that are still supercooled at that temperature than they are for the Arctic Ocean. Presumably because, in part, of a higher concentration of ice nucleating particles. Now, the second natural experiment then that we can use to figure out if seeding these clouds would indeed produce cooling is that within the Arctic Ocean, there's large differences in the concentration of dust as a function of space and time. So we can see how the clouds respond to that as well, as a proxy for what would happen if we did this artificially. All right, so I'm going to first, over the past year, we've made the most progress on this first question and this first experiment. So this is what I'm going to focus on the most. So we can now fill in that diagram. So on the left, we have the Southern Ocean pristine clouds. On the right, or more pristine clouds at least. And on the right, we have the Arctic Ocean, which are dustier clouds. It's still not, don't imagine like a really dusty environment, but the concentration of ice nucleating particles there is at least an order of magnitude larger than it is for the Southern Ocean on average. Okay, so my co-investigator, Lauren Zamora at the University of Maryland, has pioneered a methodology for this, for trying to tease apart the effects of aerosols on clouds. This is a gnarly problem because the effect of meteorology on clouds is generally speaking much larger than of aerosols on clouds. So we need to control very carefully for the effects of meteorology. So what we're doing is we're getting about 5 years of data from a spaceborne LiDAR and radar called CloudSat and Calypso. We're focusing on the polar nighttime, so the wintertime months, and solar zenith angle, of course, larger than 90, so the sun is below the horizon. We're focusing for now on single layer clouds below 1.5 kilometers, so these are predominantly stratus clouds. So what we do then with that data is first we separate them into profiles, so we get all these vertical profiles of the atmosphere essentially from these instruments. So we sort them into profiles over sea ice and over the open ocean, because those are quite different meteorological conditions, and of course the temperature also is very different for those two cases, which really matters for the radiative effect of these clouds. And then we use reanalysis meteorology data to sort these data, to bin these data on the meteorological parameters, at least those that we can quantify from that data. So those include the surface temperature, the air temperature at cloud level, the humidity, the pressure, static stability, vertical velocity, and the horizontal wind speed. So what we do then, so we try to bin these data as finely as we can with the amount of data that we have, so that we still have good statistics. And then we compare the bins with similar meteorological parameters from the two different hemispheres, right, from the Arctic Ocean to the Southern Ocean. And then quantify the cloud property differences between those bins. Now, within the bin, we have, say, 100 data points. We see then if the meteorological parameters can still explain a good fraction of the variability within the bin. If these meteorological variables can, then we haven't binned well, right? We haven't binned sufficiently to eliminate the meteorological variability. And then we go back and address that, particularly if any variable is indeed predictive of the variability within the bin, then we use that variable to bin on. So we use it as one of the 3 meteorological parameters then that we've been on. All right, so when we do that, we end up with a whole bunch of different bins, right, that are common between the Arctic Ocean and the Southern Hemisphere. And then we weight the difference between those bins by the number of occurrences we have in the Southern Ocean. And we do that because then what that means is from the, say we get a difference in cloud properties between the Southern Ocean and the Arctic Ocean after the weighting. What that means then is if we take those Southern Ocean clouds and we seed it to the population of aerosols in the Arctic Ocean, the cloud properties would change by that amount that we have quantified, or at least that is the hypothesis, that those changes, those differences between the Southern Ocean and the Arctic Ocean are due to the differences in the IMP levels after we control for the meteorology. Now, Lauren would like me to emphasize that these results are preliminary. A lot of them were obtained over the past few weeks, and I'd really also love input on the approach here. Okay, so I'm going to show you some plots like here in the upper right. So this will be the difference between the Southern Ocean, so the Southern Ocean minus the Arctic Ocean for similar meteorological parameters. We've been on 3 meteorological variables that we randomly permeate, right? And so we get a result for each permutation from which we can build a probability distribution. And so we then show the box plots that represent that probability distribution. So this is for glaciation. So the glaciation in the Southern Ocean minus that in the Arctic Ocean. Blue is open ocean, gray is over sea ice. And we can see indeed that the clouds in the Southern Ocean are less glaciated than for the Arctic Ocean. That's something the community has known for a while, and actually I showed that sort of in that earlier plot. This is, of course, consistent with the hypothesis behind mixed phase cloud thinning, that as you add ice nucleating particles, your clouds will glaciate. So in the pristine Southern Ocean, you would expect less glaciated clouds than in the dustier Arctic Ocean. And then let's look at the thickness of these clouds, the optical thickness of these clouds. And here we also see that the thickness of clouds in the Southern Ocean is larger. These clouds are thicker, optically thicker, than in the Arctic Ocean by around 0.15 units of optical depth. So this is again in keeping with what we expect under the mixed phase clouds thinning hypothesis. It's worth emphasizing here that these clouds are optically quite thin because we're in the Arctic. There's cold temperature, so there's not a lot of water vapor. So the average optical depth of these clouds is around 1 or so. So 0.15 is actually a substantial difference here. Now let's look at cloud prevalence, because that's also hypothesized to decrease with glaciation. We are not seeing any evidence for that. It's important to emphasize here these results are slightly different. Before we were looking specifically for profiles that had a cloud, a single layer cloud at between 0.6 to 1.5 kilometers. Now we're looking at all profiles and quantifying what fraction of those profiles have a single layer stratus cloud. And we're not seeing any differences, whereas under MCT you would expect some of these clouds to precipitate out faster, have a lower lifetime, and thus have a lower coverage of these clouds. But of course results are preliminary, but initially this results does not seem consistent with the mixed phase cloud hypothesis, or at least one of the mechanisms through which we'd want to generate a radiative forcing. Okay, so can we then answer that question of would mixed phase cloud thinning cool? Well, it's hypothesized to cool through those 2 separate mechanisms, related but separate. One is the decrease in the cloud optical depth, right? The cloud just becomes thinner, so more radiation passes through. We do observe that. We don't observe the second mechanism, that there's a decrease in the cloud fraction. So we expect then the following, that at the surface, at the bottom of the atmosphere, we would expect a higher cloud radiative effect for the pristine environment, for the Southern Ocean, because there the clouds are thicker, right? That would occur both over open ocean and over sea ice, because in both cases you just have this radiator overhead, and if that radiator is thicker, you'd get more radiation emitted downward. And we can look now at the cloud radiative effect. This is from a separate product that is calculated based on these LiDAR and radar profiles together with reanalysis data. It's called the Flux HR LiDAR product. And indeed we see here that the cloud radiative effect in the Southern Ocean is larger than it is for the Arctic Ocean for comparable meteorological conditions, by over the order of a few watts per square meter. So that's consistent with our results and the MCT hypothesis. We would also expect that because the clouds are thicker over the Arctic Ocean, the pristine environment, that there also we get a higher cloud radiative effect at top of atmosphere, and we actually do not see that. We see something that is not statistically significantly different from zero. So that's a little surprising, and we're digging into this further. And then lastly, over sea ice, the story is a little complicated because the clouds over sea ice, usually there's a temperature inversion in wintertime above the sea ice, and so the clouds above the sea ice actually are quite similar temperature to the sea ice itself. And so looking at it from top of atmosphere, it wouldn't radiatively really matter if there's a cloud or not. And so the cloud radiative effect of these clouds is very small, and so messing with them, changing them, wouldn't really affect that very small cloud radiative effect, and that's indeed what we're finding. Okay, so that's the results preliminary from the first natural experiment. We also want to do the second natural experiment, looking within the Arctic as a function of differences in dust concentration, and dust is the main ice nucleator, especially at colder temperatures for these clouds. There's a hang-up there in that, of course, we need accurate predictions of Arctic dust. That is difficult for a variety of reasons. One of them is that some of the dust there is generated locally. This is called high-latitude dust. This is not really in models. There's some models now that are starting to implement this. It's certainly not in the MERA-2 or other reanalysis meteorology data sets. So our team is first adding high-latitude dust to the next release of the MERA data set. So this is done in collaboration with scientists at NASA Goddard. And this is work led by Catherine Moore, who's here also. A postdoc in Lawrence Amora's group. So we're adding that to the MERA-2 or MERA-3 reanalysis product, and then we'll do a similar binning analysis, but now including the concentration of dust as a predictor. Okay, so can we now answer then how much cooling mixed-phase cloud thinning would provide? Well, no, not yet. Our results are not mature enough for that yet, but we are hoping to get some answers on this by next year, certainly. Our third question then of what will the benefits and the unintended costs be? We've started developing the tools mainly for addressing this for this question. For this, we're using a hierarchy of models, and this is work led by my postdoc, Shah Ali, who's also here, and supported by Amado Evan, Ian Eisenman, and Sarah Ahrens at Scripps. So we're using the community Earth system model, like several other groups here. This is a fantastic tool, super comprehensive. It's also computationally very expensive, and results can be difficult to interpret. So to help with that, we are also using an energy balance model, which of course is computationally way, way cheaper, and you can add and remove processes much more easily. So we've added a seasonal dynamic sea ice model to this. We're also going to add seasonal cloud feedbacks, which are quite important in understanding the difference between applying cooling in the wintertime versus the summertime, which is what would be predominantly be done with stratospheric aerosol injection and marine cloud brightening. So of course our goal then would be to quantify these benefits and the costs of wintertime polar cooling, especially in comparison to doing nothing, or summertime cooling, like what we get from other techniques. Two key metrics there would be looking at delaying Arctic warming, the ability to delay Arctic warming and the sea ice melt. And we'll also focus on what the implications are for folks living in the Arctic, of course. And this is done in collaboration with Diego Villanueva and his group at ETH Zurich, as they're also using the community Earth system model, as Diego will tell you in the next talk. Now, as a sort of a bonus, we are also developing high school lesson plans. This is work led by my grad student, Vanessa Machel, who's also here, in collaboration with a local teacher, Julie Alvarado, and Zachary Q, who's the co-investigator. He's at UCLA's School of Education and Information Studies. And the objective here really, is to educate the next generation on climate change and climate intervention. Maybe we'll do a better job with this generation than the previous ones. And perhaps inoculate students somewhat against the misinformation, right, we all know is swirling around about climate intervention. These lessons are almost done, And they will be taught for the first time, we're very excited, by Julie Alvarado in her classroom. The idea is to iterate them and to then make them available to all teachers across LAUSD and possibly beyond. Summary then. So my preliminary conclusion is that mixed phase cloud thinning might cool, and it's of course unclear still how much. I hope to have more clear results on this next year. We do find evidence for the mechanisms behind mixed phase cloud thinning. The clouds are less glaciated and more optically thick. We don't find that they are any less prevalent, and in terms of radiative forcing, that would probably be the heavy hitter if you actually were able to remove clouds, reduce the cloud fraction. But we're not seeing any evidence for that as of yet. We are planning to look at other cloud types. We've just far looked at stratus clouds. We might also look at other cloud types like altocumulus. We find that seeding thus far could produce cooling at the surface. That might be relevant. Other parts of the planet, the surface and the top of atmosphere are radiatively very strongly coupled. That is much less the case in the Arctic, so providing cooling at the surface might be quite helpful for keeping the sea ice frozen, for instance. We are looking at that, of course, with CESM and more advanced climate model simulations. We have conflicting results thus far at the top of atmosphere, which we will delve into further. So our goals for next year are to examine the response of other cloud types at this second natural experiment, right, of varying Arctic dust concentrations, and investigate the climate response to cooling. Thank you.